understanding the disk structure, and then we talked about, or we are talking about, the file system implementation. And in file system, there are a couple of system calls that we talked about: opening a file, closing a file, creating a file, writing, reading, and all these things. And all of these things, like all of these system calls, although they are separate and that implementation differs from whatever is in Windows, won't really work on Linux, but there are some commonalities among them. Like if you want to implement a create file command in any operating system, then you in general need this general data structures, so the generalized techniques. So we talked about these data structures, those are needed. Now, to creating a new file, an application program, user program calls the logical file system. And remember that logical file system created the directory structures, the indices. So to create a new file, it creates a new file control block, FCB, or if the file system implementation creates some file system, like all FCB, create all file control blocks at one go, at the file system creation time, then an FCB is allocated from the set of free file control blocks. In fact, in Linux, you have a settled in a partition, you have a fixed number of file control blocks, fixed number of inodes, those are created. And whenever you want to create a new file, a free FCB is allocated to the process. So this FCB creation is volume specific and aided, and this simply because it's volume specific, meaning that if you want to create a file in a file system like in C, then it will have a free, it will just take a free block, file system block, for the C drive, so C partition. The system that reads the appropriate directory into memory or use it from directory, the system is it basically reads the corresponding FCB, like whatever the FCB is given by the logical file system. The operating system will read that FCB directory in memory and updates it with the new file name and FCB and writes it back to this. What does mean? Meaning that if you want to create a folder called books within lecture materials, that means that first the application say like I want to create a folder called lecture materials, Wes will read, assign an FCB, and it will read the corresponding directory, in this case the resource lecture resources directory in memory, and update it with the new file name and FCB, add that FCB to the directory and writes the whole thing, the directory structure, back to the disk. It's like just changing, it's basically just moving pointers and adding pointers to the directory. So this is the creation mechanism. First get a free FCB, add it to the directory structure. That's it. So how does open works? So after a file is created, it must be open to do anything useful. So this open system call passes a file name to the logical file system. And this system call first searches the system-wide open file table to see if that file is already in use by another process. If that is the case, that is the file is already used by another process, then a per process open file table entry is created pointing to the existing system-wide open file table. Understand why? Because you don't really, so you have the open file comment, and essentially that would be if that file is already opened, then the system-wide open file table already have all information about the file. So you just add a pointer from the process to the system-wide open file table. If that is not the case, then the directory structure is searched for this file name, and once that is found, that file is found. File is found is meaning file found means that you exactly know within which directory at which index the FCB of the file is. And once this FCB is found, the file control block is found. The file control block FCB is copied into that system-wide open file table with number of process that called it. At first, the number of process will be just 1, then it will increase or it comes to 0. And finally, this open system call will return a pointer to the entry in this open file table. So if you have a Python code which is trying to open a file, a lot of things happen. First, the operating system checks if the file is opened by someone else. Opening by someone else means that there is a system-wide open file table. So there is an entry for that file because it's already opened. So it just so the operating system just adds a pointer in the per process open file table to the system-wide open file table. If that is not the case, then the FCB is found using the directory structure, because the remember the directory structure basically gives you an FCB which has all the information that you need, including where the data blocks are and what the metadata is and so on. So that FCB is copied in the system-wide open file table, and then from the per process open file table there is a link to the system-wide open file table. And what is you have a file descriptor to after you like as a return value of open. So what is the file descriptor? It is basically a pointer to the entry in per process open file table. So a schematic of this is here. So when you open a file name, it basically check that imagine that file is not opened by anyone else, then the directory structure would be searched. Then you will basically know the from the directory structure, you know the pointer to the file control block. You get the file control block from the disk. So this is user space where you call the open. This kernel memory which holds the directory structure. The secondary storage which holds the file control block. This file control block essentially would be then copied to the system-wide open file table. Now the file is opened. So how to do the operations on the file? So let's talk about read, the most basic one, reading data from the file, and the basic schematic of how it works is similar. So you have the read call, right? And you have the file ID. So what does the ID is? That ID is basically index of the per process open file table, which means that read and then file descriptor, or this is basically you have the read in the index, you have the read file descriptor. That is how you read, or in Python it's basically f.read. But essentially you need to use the file descriptor read. Why? Because this file descriptor is nothing but this index here, which means the index, the array index in the per process open file table. And that array index points to the system-wide open file table. And this system-wide open file table have all information about file control blocks and the data blocks. So system-wide open file table, essentially via file control block, FCB knows that where the data blocks are. So essentially the read call passes the file descriptor, and using this per process open file entry index, enter at index points, you get the system-wide open file table. There are two open file tables, meaning that open file tables basically it's like per process and system. You generally go to the file table for sorry about that. So this is essentially goes for goes to from per process open file table, it will go to system-wide open file table, and then pass the information to the file organization module and the layers below, because now I know after this read call exactly where to write or what to read the data from, and that is the job. Remember the layered structure, that is the job of the lower levels, where the file organization module and finally device driver will read data. So while reading this file, also remember that there's like we talked about, say, like to make it faster, in-memory buffers are also used to hold file system blocks so that the process becomes faster. This again for The reason is that using such in-memory buffer, you'd exploit the locality of data. So now we know how to create the file, essentially manipulate the file entry pointers into system-wide and purpose open file table. We know how to open work, similar things. And now, after read, we'll talk about how can we close the file. That's yet another system call, right? So when a process closes the file, the per process table file entry is removed. And the system-wide ones, that is the system-wide ones, remember that has pointed to the actual FCB and has a count that how many of this how many processes open that file. So if one of the processes called close, then the open count is decreased by 1. And if the system-wide open table country is 0, meaning no one has that file opened, then any updated metadata is copied back to the disk, to a secondary storage, and the system-wide and the entry would be removed. So what is basically the takeaway till now? Essentially, you have two open file table entries. Tables. One is per process, which is each process has an open file table, which is nothing but an array, like C array. And then you have a system-wide open file table, again a C array. Like you can think of abstractly as a C array. Now, in any case, like whenever you want to create a file, you actually create a file by finding free FCBs. You open a file, you start from the per process, and you go to the system-wide, and then the system-wide open file table knows where the data blocks are to read or write and everything. And in close, you can only close a file if no other program has it opened. So my main point is that primarily these open file tables are the data structures which you use for implementing your system calls in file system. So some systems actually use this file system as an interface to other system aspects even. And essentially this open, close, read, write, they're intuitively that makes sense. You're opening a file, you're reading a file, you're writing to a file. Intuitively makes sense. So that's why operating systems like Unix or Linux provides exactly same abstractions also for other things like networking. Or basically it actually does like opening a keyboard or reading from keyboard, writing to keyboard, exactly same abstractions. And the system-wide essentially open file table, like if you're going to real implementation, you remember the system-wide open file table means like whichever file table, like whichever FCBs are in use currently. But in general, in Linux, the system-wide open file table entries, they are not only FCB or inodes, they're not only actual files that you learned so far, but they are also network connections and devices. And this particular abstraction, that everything, like every device or network or file, you think like in terms of open, close, read, write, this type of generalized system calls. Due to this, there is this term called everything is a file in Linux, and there is a wiki page for that. I put the wiki page here. You can search everything is a file Linux, and you should get the first hit should be the wiki page. But essentially, from the point of the point is that from a user point of view, if you know how to do open, close, read, or write in operating system, then you can actually use that knowledge. I mean, that kind of function calls for almost everything, including a file, a network connection, or a device. Now, so far we talked about like file implementation, two open file tables, system-wide process, and just telling that this was so popular that Linux developers actually, Linux developer, Linus Torvalds, or even other developers decided that everything should be a file in Linux. And what does it mean? Everything should have this same open, close, read, or write operands on them. However, we actually we didn't talk about one aspect quite clearly, which is we talked about the in-memory buffers and caching and directory caching and all this. But the thing is that requires some more attention. The caching aspects of file systems are extremely important. Like most systems keep all this information about an open file, like all the metadata, not the exact actual data, but all the files about an open file in the main memory in RAM. The reason is that reading from disk and writing to disk is slow. So RAM or main memory is faster than secondary memory. So by reading the information from disk, the whole directory structure and the data blocks in the only once, and then keeping it in memory till it's used, one can speed up everything except for the first read. Of course, you have to read and put it into memory, but then you can actually use this in-memory buffer cache for both read and write, because whatever is read now, possibly it will be read again. And wherever it is written, whichever block, it will possibly written again. In fact, the average, so people actually wrote papers on this, but average file system cache hit rate is 85%, extremely high. So essentially, the point is that in file system, you often if you think of most of the system calls that we deal with in those actual implementations, you should have in-memory buffer cache for both keeping the blocks that you just read or the address of the blocks that you just wrote to. They would be used once again. Any questions so far? Okay. So we are talking about essentially, we so far talked about the implementation, in general, the implementation of this system calls. Now let's talk about, so you know that how to create a file now. Basically a file is just data blocks on disk, and the directory and the FCB is the metadata associated with the file. And we talked about that for open, close, read, write, create, for all of these calls, system calls for a file, how can you manipulate the FCBs and do pointer manipulation and adjust the system-wide as well as process open file table to do this thing, to actually efficiently read and write data using files. Now, in any one of this open or create or read or write, you actually needed to look up the FCB. You need to know that where the file control block is, which has the metadata and also addresses of the data on the actual data blocks, the data of the file. So for that, you need directories. So the directory, what is the method? So because we are talking about this file system implementation, we need to talk about implementing a directory. And the simplest method of implementing a directory is to use a linear list of file names with pointers to the data blocks. Meaning that you have a directory, you need to look up the data blocks where the FCB is, and the FCB has pointers to where the data, actual data blocks are. So for that, you can just use a linear list. The problem is that if you just have a linear list, if you, linear list means like all you need to know that how to translate your file name into the FCB. So directory is the lookup for that. It's simple to program. However, if you want to search a name, it will be O of n search time. You need to, in the worst case, you need to scan the whole list. So it becomes time consuming. So what people did was that, you can still keep you can still keep an entry, or you can still keep the directory as a mapping from names to the data blocks or to the FCB, but you can keep it as a ordered list so that you can use a binary search, or you can use a B plus tree, which will make searching easier. So now you would actually use, the whole idea is to use a efficient data structure, which will allow you to search for a file name to its blocks. Another improvement over the linear list. So these are improvement over linear list. You just have a linear list of file names to the data blocks, but you can use sorted list or sorted links, or use B plus tree. However, there is another improvement, a simpler improvement over linked list, which is via hash table data structure. And in this method, a linear list stores the directory entries, but additionally, a hash data structure is also used. What does the hash table contain? It's a hash table takes a value from the file name, like the hash of the file name, and returns a pointer to the file name in the linear list. So it's like a lookup. For example, if you have a linear list, then you have a hash table for looking up that given a file name, which entry of the linear table do you want to check. It decreases the directory search time considerably, but the problem there is that there might be situations where there are collisions, where two file names hash the same location in the linear list. That is one problem. And another problem is that if the linear list size is fixed, only then you can use it. Or you can use chained overflow method, which will become slower. So the whole reason of using a special hash table plus the linear list is that there has to be a linear list, but to efficient searching, we'll create a hash table so that I would know that given a file structure, which entry of the linear list should I look up. So the problem with fixed table essentially means, just to actually take it for a moment, take a moment to understand it. Entries are fixed size essentially mean the linear list or file names are fixed size, which means that you can only create 1,000, 100, or some X number of files in a directory. On the other hand, the chained overflow method would possibly just use a linked list data structure, which will to increase the number of file, like for each file name, number of section, number of indices of the linear list to probe. But then again, the linked lists are anyway slow, the chains. But it will be still faster than linear search. So tell me this hash table, right? This will make all of a sudden, it will make the linear looking up the linear list or finding names in the linear list faster. What is the trade-off here? Because in systems you cannot get anything if you don't spend something. So what is the trade-off when you use a hash table to speed up searching a name in a linear list? What are you trading off for this performance? This is there is a space time trade-off. And what is the trade-off? Like how much memory are we, or how much space are we sacrificing? If there are n files. Essentially, it's at least 2 of name, because for each file name, you need to create. Yes, that's a better answer, Mukul. The space consumed for the hash table increases linearly with the number of files. Yeah, perfect. So this is a stupid method, but it sort of like works. Uh, so the direct access essentially nature. I mean, basically this. Now we are talking about like in the directory structure, like allocation method, which basically means that so now we have a linear list, and linear list can be improved using linked list or B+3, so that you can look it up. B+3 is fairly fast, and then you can use hash table, which is in very popular demand. But each one of them, you need to use the FCB, and the FCB actually points to a bunch of data blocks for a particular file. Now the question is, how would you allocate those free data blocks to a particular request? There has to be an algorithm for that. You cannot randomly give that. So essentially, we will now discuss mechanism to allocate the space, the data blocks on secondary storages for each file. When you are creating a file, when you're appending a file, when you're writing more and more data to a file. So essentially, there are three major methods of allocating disk space: uh, contiguous allocation, linked allocation, and indexed allocation. We'll go over them each one by one. But the thing is that a system uses one method for all files within a particular file system type. So what is the problem that we need to solve here? We have a bunch of free data blocks, and we have a bunch of free data blocks, and we have a bunch of files to create, and we want to know how to assign these data blocks to the file FCBs in the file control blocks. So contiguous allocation requires that all blocks of a file should be kept together contiguously. What does that mean? That means the performance is extremely fast, because in FCB, you just say that start reading from 1, 2, 3, 4, 5, 6 block and read 30 blocks. That's it, done. And this is extremely fast because it is just taking contiguous, it is reading contiguous blocks of memory rather than looking up again and again where the blocks are. Because in general, reading successive blocks of the same file requires no movement of disk heads. Just now think about it in a more physical sense, that because you might actually have a fuzzy warm idea that if I have contiguous memory assigned or blocks assigned to a particular process, it will be faster. But the main reason is that, I mean, if you think about a hard disk that many of us still use, it means that if you're just reading contiguous spaces, then your head doesn't need to move and go to another track. So it gives the best performance in most cases. And it is simple because only starting location and length is required, and then you can just read it. So contiguous allocation of a file is defined by the disk address of the first block and the length. Let's take an example of the contiguous allocation, right? I think I should have this. So in this diagram, we are like for each file, right? From here, just see this now. So this is your hard disk. Basically, it's a cylinder, and there are these tracks, and there are different sectors also. But the point is that if you think of this, if you don't really, if you forget about the physical properties and see there are only blocks like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on in these blocks. And in contiguous allocation, what happens here? It's basically like it starts from the first one count. It starts from 0 and goes for 2 blocks. Count, start, length 2. Mail starts at length 19, length is 6. 19, and then length is
1, 2, 3, 4, 5, 6. This is the main file. File F starts from 6, have a length 2, 6 and 7. So this is the good part of contiguous allocation. Extremely simple to implement, as you can imagine. You have just the block IDs and you will just store the start and length, and that's it. You're done. Now, let's actually see that how exactly actually mapping from logical address to physical address goes in this contiguous allocation, the mapping part. Now, what is the logical address here? When you want to access a portion in a file in this method, you would say that I want to access fifth line in note.txt. Okay. Or more generally, for example, like it is like your application would possibly, like your text reader, like you would say that I want to read fifth line, and the text reader interprets that read from 75th or 77th byte in a file. So if you assume this logical address or LA is basically, it actually means that in the general sense it will be useful for your exams also. But essentially, when you say the logical address LA, it means that you want to access LAth byte of a file. That's the most general thing, right? You basically say that I have a file and your application can say that I read the 7th byte, 6th byte, and so on. And then your application can tell you as the user or some other user that, look, if you want, I mean, so you can just tell me that which line do you want to read, and I'll convert it to byte number. So in this case, if you assume that the physical block size is 512, the physical blocks, the blocks are basically 512, then we need to know the physical block number of the LAth byte, and we want to know the displacement within the block to start our disk operation, like start our reading or writing. So essentially, you'd compute in this way. You want to read LAth byte. So what is the block number? LA double division is integer division by 512. So you get the block where the actual data resides. And then within that data, you would actually look into how many bytes do you want to go up, because this doesn't really give you that within 512 byte, like it will just put your pointer at the start of a block. But within that block, which byte do you want to read or write from, or read from or write to? That will give by this R. So this is quotient and reminder, short for Q and R. But if you get this, then the physical block to be addressed would be Q plus starting address. So if you start from 0 or start from 2, then you go to, or basically if you start from second block, then the physical block, the second physical block, then you'll go to 2 plus Q. That will give you the resulting block where you want to do your read or write operation, and you should start your read or write operation within that block by R bytes. So this is the contiguous allocation scheme mapping between the logical address that the application knows, like LAth byte to read or write in a file, to the physical address, because physical address understands in the block name 512 byte blocks. So contiguous allocation makes things much simpler. You can just use integer divisions without any worry about most of the stuff about where the fee blocks are and all these things. So let's actually look into the implementation issues of such allocation, because everything comes with a cost. The main cost is that how to find contiguous spaces. You know, if your file is 2 GB, you need to find 2 GB continuous space in your data block, in data blocks on your machine, on your storage. That might seem hard. So essentially, you need to find space or find contiguous space for files, and oftentimes there is finding space for this contiguous allocation basically boils down to the fact that you have a file size and sets of fee blocks, And then you need to know that which like where to actually put those bytes. Right? So you can actually choose the first fit or basically best fit case. First fit meaning that the first contiguous space that you will get, you will put there. Or best fit essentially means that you will choose the space where like where you would actually like you will only take that contiguous blocks which will not waste any space for your file. If you want to write 50 bytes, you will find a block which has only 50 bytes. However, both of these for best and first fit, I am not putting it in the slides because both of them has the same problem of external fragmentation. So your job is to find the first address where you have 50 byte of free space if you want to do contiguous allocation of 50 bytes. However, the external fragmentation problem means that as files are created and deleted, meaning that data blocks are allocated and destroyed, the free disk space is broken into little pieces. And external fragmentation exists whenever free space, whatever you have, is broken into chunks, and no chunk is big enough to hold a file. But together, if you make those chunks together, then there is enough space for writing a file. So how do you know if external fragmentation is a problem or not? If your largest contiguous chunk is insufficient for a request or sufficient for a request. If it is insufficient, then external fragmentation actually made your data blocks pretty unusable. So what is the solution to the external fragmentation? Essentially, you can know like you should be know the size of the file. So that might be one, because you can essentially, so basically, okay, first you can actually put it not even knowing the size of file. That is more hard. This is more smarter. So what you can do is that if you have too much external fragmentation, then you can actually put this compaction offline or downtime. Basically, you need to actually copy the whole file system into another disk where there are more free space. That is possible. You can buy, like if you have 1 terabyte disk space, you buy it for 4 terabyte one and you copy your own file system. Okay. So if that is the case, then the original file will be freed completely and creating one large disk free space, and then you copy the file back into 1 terabyte file drive like one after another, because now you have the exact number of the files, you know what the exact size is. So using the 4 terabyte buffer, or even you can use like 1 terabyte, if you have a 1 terabyte file system, you can use a 1 terabyte buffer, you copy it and then you copy and format that partition and then write it back, making a like doing it one after another in the contiguous allocation. So this scheme effectively compacts all free space into one contiguous space and then push the files there. So some systems might actually want this function to be done offline with the file system unmounted, and during this time normal file system cannot be accessed. Most normal file systems can do it online. You can do something called defragmentation, which is basically this your compaction, but it is often very expensive. What does defragmentation do? It has this smarter online method where you try to actually find out this large files, you copy it to somewhere else, like in some swap space, and then you will create this nice contiguous memory space and you start writing them from the swap space to the contiguous space. This is also called defragmentation, but it's extremely expensive, and this sometimes damages your hard disk because you are reading and writing quite a bit on your disk. You're moving and creating a contiguous space and writing it there. So it's expensive. Now in contiguous allocation, another problem is the file size. when the file is created, the total amount of space it will need must be found and allocated, right? Now in contiguous allocation, the point there. So now in practical cases where, I mean, you can keep increasing a file, right? Think about all this huge like codes that you write. It's generally the file size just go on increasing. And ideally a file can be as big as the whole free space. However, in a contiguous allocation, at the beginning you allocate those free blocks. So when you try to improve it or increase it more, if there is no space, what would happen? You cannot increase the size of the file. And in general, knowing of the size of the output file must be difficult. It is difficult. So if we allocate too little space to a file, then we can find that the file cannot be extended in a contiguous allocation. Or if we just make it too big, then the space will be, then there will be external fragmentation and the space will be wasted, which will again want to do you. The solution of external fragmentation is compaction of files, creating a contiguous space and then pushing the existing files there, which is expensive. So essentially, you can terminate the program that is using those files. You can then essentially like reach for whatever programs or whatever files are using contiguous space. You can delete those files and then you can assign contiguous space. But this is basically costly and this is heuristic. This doesn't work. And even if you overestimate the space, external fragmentation still costly. And if you don't know the size of the file, then you might want to find another larger space and copy the current content, like your compaction. Basically, you have 50 byte free space. You want to write 50 bytes more to it. So you find a 100 bytes free space and write the new data and the old data together. Again, it's slow, and no one told you that that kind of you can find out that much free space. So contiguous allocation is extremely simple and effective, but it also comes with a plethora of problems, mainly because for contiguous allocation, you need to make sure, I mean, getting continuous space as a system is used by the multiple users again and again, it becomes hard. So contiguous allocation is effective and performance wise good, but assigning contiguous space to files as more and more files are created in a system becomes problematic. External fragmentation is a big problem, and now you know what is external fragmentation. There is free space, but the smallest contiguous chunk or the biggest contiguous chunk is not enough to write a file. So the linked list allocation solves all the problems of contiguous allocation. With linked allocation, each file is a linked list of disk blocks, and these disk blocks must be may be scattered anywhere in the disk. What does it mean? Like, you don't really think of now this file blocks as a contiguous space, but rather a linked list. It's not an array, it's a linked list. Okay. So the directory contains a pointer to the first and last blocks of the file, and each block contains a pointer to the next block. These pointers are internal for the operating system, of course. So if each block is 512 bytes in size and disk address is 4 bytes, then the user sees the blocks of 508 bytes. Okay. So essentially, if a block is 512 bytes, then 4 bytes, a 4-byte pointer for each block is stored to point to the next block. Clearly, the file when the file ends, so in the last data block will go to a null pointer, of course. There is definitely external fragmentation because we are not really talking about contiguous allocation. And each block contains pointer to the next block, and essentially you call your operating system calls the free space management system when new block is needed. So it will look into the free block and adjust the pointer. It doesn't require any compaction or defragmentation, because it doesn't have any external fragmentation. Now the problem is that in the contiguous allocation, you you really didn't need to traverse all the pointers to access read data blocks. Here you do need to. So essentially, what it means is that it's like allocating, like if you're having random access, then you have, or this within this data blocks, like read 75th byte, 100 byte, and then 150th byte or second byte, then it becomes really slow, because you need to do a linear search. We are talking about linked list here, which will take multiple IOs to the disk device, and that means slowness. Another big problem with linked allocation is the reliability, meaning that if one single pointer is damaged, your whole file is not readable anymore, or at least readable up to the point of the damage, but not after that. So one way to improve the search efficiency is to cluster blocks and then use a linked list structure on those clusters. So you have a small contiguous blocks of data, and each one of them are basically connected with lists. But it will increase internal fragmentation. External fragmentation is where there are free spaces within the contiguous free spaces, which are small individually, but together they are big enough. Internal fragmentation is within a block itself, 512 byte, there is much space which is wasted, nothing is written there. This will happen here if we cluster the blocks into groups and then use linked list at the end of those groups, simply because not the whole group would be used for assigning a file. So let's give an example, right? So it's basically again a linked allocation. So the file is zip. It starts at 9 and ends at 25. So you start with the 9th block, 0, 1, 2, 3, 5, 7, 8, 9th block, which has which basically tells like you should go to the start is 9th block, which has this 1, and then you will again go to 1, which I think this is mistake here. So essentially block 1, 2. Okay, I see. So but there is a mistake here, I guess. So for 9, you would first go to block. You will first actually talk about going to block 1. So you will go to 1, and then this is 1, and this should actually be going to block 10. Okay, so in linked allocation, you need to. I think this is. I'm sorry, this is a bit messed up about following this link. So for file zip, it will start with directory 9 and sorry, the block 9, and will end at 25. So 25 has a null pointer, and 9 has the first. I mean, it is basically 9th block should have the next block's address, like wherever it is pointed to. So it will essentially, this 9 would go to 16, they need to go to 1, and then 2, and then 25. Okay, got it. So sorry, that was a mistake. So I thought that we wrote this names of the values here, but rather this is the content of the file. So first you will start with 9th block. The 9th block, the pointer of the 9th block will point to the 16th block. 16th block will point to the first block. The first block will point to the second block. Second block will point to the 25th block. And finally, -1 here points that it will be the end of the file. These values here, like 1, 2, 1, and then null value and all this, these are basically values of the data elements in the file itself. So these are pointers using which you would actually go in a linked allocation to the next block. And these values here are basically values, the contents of the file itself.
Sorry for the confusion, but is that clear? Like if you follow this, these are basically next pointers, and finally linked allocation will end at block 25 here, which is the block end block, which is written here too, like in the directory structure also. Is there a confusion? Like, is there like, do you have any questions on this? Because I know that this is something there is a confusion, at least for me, on this. But basically, you just follow the link structures, and these are pointers, and these are the values of the data file. Any questions here? Okay, so this linked allocation solves the problem of contiguous allocation, but it actually creates additional problem of lookup and performance. So essentially, let's take an example of each block with this linked allocation scheme. Like if you go into each block of there, then each file is a linked list of disk blocks. So the block has a pointer and the data. And again, if I tell you that I need to access 75th byte of a particular file, which is my logical address, how to map it to physical address? So remember that here, each of these data blocks here essentially have only 508 bytes to write, right? Because some portion is reserved for the pointer. So you need to go to, like, if you want to 75th byte, like readable, actually manipulatable byte, then you need to go to LA divide by 508th block. So you have to follow the pointers this many times. And then once you get to that block, that qth block in the linked chain, you do a displacement within that block to find the 75th byte. So that is LA mod 508. And remember that there is a pointer in the each block. So the actual displacement is that R plus 4. Because you need to address the last block's pointer. This is assuming there is a 4-byte pointer. That's why 512 minus 4 is 508. So you only 508 corresponds to only this space. So this is why this is, you want to actually go for this extra 4 bytes. This is for the pointer. Now, to give you a practical example, and this is important, generally this allocation method, the linked allocation method, is used in FAT and FAT32 variation specifically. So in general, it is used in MS-DOS and OS by 2 operating systems. And this FAT, I mean, this file allocation table is similar to a linked list, essentially. What does it have? This table has one entry for each disk block and is indexed by block number. So there is a beginning of the volume has a table which is indexed by block number, which is like a linked list, but it uses cache and hash tables and all these things. It is faster on disk. And essentially it does for a new essentially it contains the directory entry, contains the block number of the first block of the file. And I mean, when you're talking about the linked list structure, it means that the table entry indexed by the block number contains the block number of the next block of the file. It follows this chain, and essentially it will continue till the end of file value is reached.
And an unused block is indicated by a table value of 0, allocating a new block to a file. So here's let's take an example of the FAT structure. That will be better. So here for the file name test, so there is a file name test, right? We show the directory entry, which is identifying 217 as a start block. And this is your file allocation table FAT, where the whole FAT, the file system name came from. So 217 is your start block. So you go to 217. Now, FAT table gives you all the blocks for the table. The entry for 2007 index in FAT table is 618. So the next block is 618. Okay, this is your 618th block. And when you go there, it's 339th block. So you go to 339. This is how. So you start from 2017, and in 217, and in 217, you know exactly which block next to go to. This FAT allocation scheme can result in a significant number of disk head seeks, because first you need to go to 217, then to 218, and 339, and so on and so forth. Right? Unless the FAT is cached, so the FAT is cached in general. So the file allocation table essentially means that you have just like a linked list structure, but you have a special table which tells you exactly what next block to go to instead of saving the pointer. So here is a question for you in this file allocation table. This is a homework question, and expect similar questions in the exams. But so the question is that you have 512 GB hard disk, and each block size is 4 kilobyte. Okay, and if your file system contains a file allocation table, this is the table which basically talks about the lookup, like what is the next entry of that file. It starts with 217th block. Then, because in the file allocation table, this entry is 718, it will go to 718th block, which contains 339. So it will go to 339th block. So we want to know that what is the size of this table. If you have a 512 GB hard disk and each block size is 4 kilobyte, not 512 anymore, 4 kilobyte, what is the smallest amount of memory? I'll give you the answer right now, around 432 MB, but try this as a homework. 512 hard disk space, each block 4 KB. What is the size of the file allocation table? Okay, this with FAT. So we talked about two allocations of data blocks. One is contiguous and this linked list, and this file allocation table, which is a special variation of linked list but faster because you have a file allocation table or FAT. And we end with this question that 512 GB hard disk space, each block 4 kilobyte. What is the size of the FAT? So we'll continue tomorrow from here in the, so we'll talk about the last allocation method, which is the indexed allocation. Okay, thank you. And if you have any questions, feel free to do. Otherwise, we would talk tomorrow. Stopping the recording.